You ever look up at the night sky and feel this strange tug, this sense that we cannot possibly be alone out here? It is one of the oldest feelings a human being can have. And I want to take that feeling seriously because it deserves a serious answer, not a hand wave, not a shrug. The universe is genuinely enormous, and we need to actually sit with what that word enormous means before we can say anything honest about aliens. So let us start with something you can hold in your head. The nearest star to our sun is Proxima Centauri. It is about 4 light years away. Now, a light year is the distance light travels in 1 year, and light moves at roughly 300,000 kilometers every single second. You know how fast that is. In 1 second, light goes from here to the moon and back again, with room to spare. In 8 minutes, it crosses the entire distance from the sun to the Earth. And yet to reach Proxima Centauri, that same light needs to travel for 4 full years without stopping. That is the nearest one. That is the closest star we have got. Now, our fastest spacecraft, Voyager 1, which we launched in 1977, and which is the most distant human-made object in existence, is traveling at roughly 17 kilometers per second. That sounds fast. It is fast by any human standard. But at that speed, it would take Voyager about 73,000 years just to reach Proxima Centauri. Not to explore it, not to orbit it, just to arrive. And here is where I want you to really pay attention, because this is the part that tends to slide off people like water off a roof. Proxima Centauri is the closest star. The Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. The distance from one side of the Milky Way to the other is roughly 100,000 light years. So, if Proxima Centauri at 4 light years requires 73,000 years of travel at Voyager speed, then crossing the entire galaxy would take something like 1.8 billion years. At the speed of our best rocket, 1.8 billion years. But wait, you say, we will build faster ships. Fair enough. Let us be generous. Let us say we build a ship that travels at 10% of the speed of light. That is an extraordinary achievement. Nothing in our engineering history comes close, but let us just grant it. At 10% of light speed, crossing the Milky Way still takes 1 million years, and that is just our galaxy. There are roughly 2 trillion galaxies in the observable universe. 2 trillion. The nearest large galaxy to ours, Andromeda, is about 2.5 million light years away. Even at 10% of light speed, that is a 25 million year journey. One way. Now, I want you to hold all of that in mind, because it is the foundation of everything. The universe is not just big, it is big in a way that punishes ambition. And this brings us to what the Italian-American physicist Enrico Fermi famously wondered about over lunch one day in 1950. He was talking with some colleagues, and the conversation drifted to flying saucers and the possibility of extraterrestrial life, and Fermi suddenly asked, quite simply, where is everybody? That question became known as the Fermi Paradox, and it has been bothering scientists ever since. Here is the logic behind it. The universe is about 13.8 billion years old. Our sun is about 4.5 billion years old, which means there are stars out there that are 2, 3, 4 times older than our sun. If life appeared around any of those older stars, it had billions of extra years of head start. Billions. And if even one civilization among the hundreds of billions of star systems in the galaxy had developed space travel even modestly better than ours and started spreading outward at even 1% of the speed of light, they could have colonized the entire Milky Way in about 10 million years. 10 million years sounds like a lot to you and me, but it is just a tiny sliver of the 13 billion years this galaxy has existed. So here is the brutal arithmetic. If civilizations are common, at least one of them should have had the time to fill the galaxy, and we should see evidence of that. Radio signals, megastructures around stars, some sign of organized energy use on a cosmic scale. We have been listening with radio telescopes since 1960, scanning frequency after frequency, and we have picked up exactly nothing that is held up as a genuine signal. The sky is quiet, suspiciously, hauntingly quiet. Scientists have come up with a long list of possible explanations. Maybe life is extraordinarily rare. Maybe the chemistry that produced the first self-replicating molecule here on Earth was a 1 in a quadrillion fluke. Life has existed on this planet for about 3.5 billion years. But for almost all of that time, it was single-celled microbes. Complex multicellular life only showed up about 600 million years ago. And technological civilizations, meaning the kind that can build radio telescopes or rockets, that is brand new. We have been doing this for maybe 100 years out of a 3.5 billion-year biological history. Maybe getting from simple chemistry to complex technology involves dozens of incredibly improbable steps, any one of which is so unlikely that most planets never clear all of them. This idea has a name. Scientists call it the Great Filter. The concept is that somewhere between dead chemistry and galaxy-spanning civilization, there is at least one barrier so difficult to cross that almost nothing makes it through. And here is the uncomfortable part. We do not know where that filter sits. If it is behind us, meaning life itself was the hard part, or the jump to complex cells, or the development of nervous systems, then we may genuinely be alone, or nearly alone in the galaxy, and the quietness of the sky makes sense. But if the Great Filter is ahead of us, meaning civilizations typically destroy themselves or hit some technological wall after reaching our level, then the silence is not reassuring at all. It is a warning. There is also the sheer problem of detection to reckon with. Even if we assume there are other civilizations out there broadcasting signals, think about what that actually requires from both sides. They have to be transmitting in a direction that happens to include us. They have to be using a frequency we are looking at. The signal has to be strong enough to survive crossing hundreds or thousands of light years without becoming indistinguishable from background noise. And we have to be listening at exactly the right moment. A civilization that broadcast for 1,000 years and then went silent would have left a signal moving outward at the speed of light. That signal is now a sphere, 1,000 light years thick, expanding through the galaxy. Finding it would require pointing your antenna at just the right patch of sky at just the right time. The odds are not in anyone's favor. And then there is the speed of light problem again, which really is the deepest problem of all. Because even if we found a clear, unambiguous signal from a civilization 400 light years away, which would be thrilling beyond description, a conversation with them would involve 800 years per exchange. Hello sent, 400 years pass. Hello back, received. Another 400 years to reply. You cannot conduct a relationship across that kind of gap. You can barely conduct a history. Einstein's special theory of relativity makes this worse, not better. Nothing with mass can accelerate to the speed of light, let alone exceed it. The reason is buried in the mathematics of how energy and mass relate. As you accelerate an object, its effective mass increases. The closer you get to the speed of light, the more energy is required to push it further, and the curve is not gentle. It goes to infinity. Meaning you would need infinite energy to push even a single electron all the way up to light speed, let alone a spaceship full of passengers. So you cannot just build a bigger engine and solve this. The constraint is not engineering, it is geometry and physics at the most fundamental level. Now some people will say, what about wormholes? What about folding space? These are not crazy ideas. General relativity, Einstein's theory of gravity, actually does permit mathematical solutions that look like tunnels through spacetime. But there is a long walk between a mathematical solution and a physical reality you can use. Wormholes, if they exist at all, appear to be subatomically small and vanishingly unstable. The kind of exotic matter you would need to hold one open long enough to pass through almost certainly does not exist in the quantities required and may not exist at all in the configuration required. We are talking about a speculative structure maintained by a hypothetical substance doing something that we have never observed any material do. That is a lot of maybes stacked on top of each other. But let us say a civilization figured all that out. Let us say they solved every problem we have not solved and built ships that can cross stellar distances in reasonable time. Now think about what they would find at the end of that journey. Stars have planets, yes, but the conditions for life as we understand it, liquid water, the right chemical mix, stable temperatures over billions of years, those conditions are not universal. They may not even be common. Our sun sits in what is called the habitable zone calculations, not too close and not too far. But even within that zone, a planet needs an active geology, a magnetic field to deflect radiation, a moon perhaps to stabilize its axial tilt, the right nitrogen-oxygen atmosphere. The list of requirements gets long very quickly, and complex intelligent life adds more requirements still. The dinosaurs dominated Earth for 160 million years and never built a radio telescope. Intelligence is not an inevitable outcome of evolution. It is one possible path out of millions. The octopus is extraordinarily intelligent by any measure and has been for a long time, and it has shown no signs of developing symbolic mathematics. Intelligence is a useful adaptation in certain environments. But the specific kind of intelligence that produces particle accelerators and space programs requires a particular social structure, a particular kind of hand, particular pressure toward long-term planning, and a lot of lucky historical accidents. Our situation on Earth involved the right asteroid at the right time, wiping out the right competitors. Change any one of those variables, and you get a very different planet. So what do we actually know? We know the universe is incomprehensibly large. We know it is old enough to have produced technological civilizations billions of years ago. We know we have not heard from any. We know the physics of travel and communication across interstellar distances is brutally punishing. We know the conditions for life like ours may be rare. And we know that intelligence, the kind that can contemplate its own existence and wonder about the stars, is not guaranteed by time or chemistry alone. What we do not know is where we fall in that story. Are we a fluke, an accident of extraordinary improbability in an otherwise lifeless cosmos? Or are we part of a universe that has produced countless civilizations, all of whom are trapped behind the same wall of light, speed, and distance and silence? Both possibilities are staggering. Both should make you feel something when you look up at the sky on a clear night. The math does not lie. It does not care about what we want to be true. And what the math says is this: even in a universe with 100 billion trillion stars, the distances between them are so vast, the requirements for life so specific, the physics of travel so unforgiving, that two civilizations finding each other may be the hardest thing the universe ever asks of matter. We may spend the entire life of our civilization looking outward and hearing nothing but the soft static of an ancient cosmos. That is not a defeat. That is the honest answer to an honest question. And I think honest answers, even uncomfortable ones, are worth more than comfortable stories that do not hold up to the numbers.